All right, here we go. We've got properties of water. It's going to be chapter 2, section 1 and section 2. The truth is, section 1 is actually just basic chemistry. And of course, that's going to be fundamental in your understanding of what water is and how it's important. So let's go ahead and do that first. We'll do the chemistry and then we'll move on to the actual properties of water. Of course, you know, water is essential, and everything that makes you up actually in some way kind of depends on how water works or how it acts. All life processes, of course, have to take place in a watery environment. We call these aqueous solutions. Most things in biology we deal with are going to be done in a solution, and the base of that is going to be water. And we'll talk about exactly what that means when water is part of a solution. Now, the shape of water is going to be really, really fundamental in understanding why it works in your body. And basically, when we get to it, you'll see that it looks like Mickey Mouse, but there's a reason that it looks like Mickey Mouse. So, like I was saying, let's go ahead and talk about the chemistry first before we really understand these major concepts about water. Atoms. You should know, hopefully you've already started this course understanding that there are things in this world, in this universe, that make up everything, and those basic things are going to be called atoms. And atoms basically are made of three parts. There are going to be neutrons, protons, and electrons. Now, the center of the atom is called the nucleus. You can see in our diagram here, we have two different colored balls kind of resting in the middle there. The blue ones are going to represent the protons, which have a positive charge, and the red ones are going to represent the neutrons, which have no charge. They're neutral, hence their name. The electrons are going to be found on the outside, kind of orbiting around that nucleus. Think of it kind of like a little solar system, right? You'll even see there's some concentric rings in there, right? They fit inside of each other. The key thing I want you to notice here is that there are three rings that we see. And in that first ring we find here, we're going to see that there's two dots. Okay, those two dots represent the two electrons, and we're going to say this first ring can hold up to 2 electrons. On the next ring out here, you could count them up if you wanted to, but you would see that there are actually 8. And then on that third ring, you're going to find that there are also 8. So those numbers, 2, 8, and 8, working from the inward to the out, is going to be really important to remember to understanding how some atoms act. But one thing I'd like to show you is going to be found here on the next slide. That basic information that we just talked about in the last is pretty much sitting there for you now. So protons, once again, are positive, neutrons, neutral, electrons, negative, and that middle portion, that nucleus, is filled with the protons and neutrons. Generally speaking, I'm not speaking in certainties here, but usually you find that you have the same number of protons and neutrons, but there are exceptions, of course. One very common exception is going to be found in hydrogen, which is the most simple element we have. It only has 1 proton in the middle and 1 electron on the outside with no neutrons next to the protons. And of course there are variations called isotopes, which are used for like radioactive tracing and some other purposes, at least by us. And electrons, once again, are found on the outside. We call that the electron cloud, just because you can't really see the individual electrons just swinging around. It's not like they're very big, and they're moving very quickly. So sometimes we reference this as a shell, and we start talking about valence shells, which we'll talk about very shortly. Just a few more models to help you understand kind of what an atom looks like. You've probably seen what we just actually talked about previously was basically the planetary model. And the planetary model just kind of shows, okay, there's a center nucleus. That's going to be He in our example up here. He is going to represent helium. And helium is just one of those, it's actually the very first noble gas, and it's a very stable atom. You can see outside we have a ring with 2 electrons there, and you can see it's the first ring because it's the closest to the nucleus and we only see 1 ring, and we'd assume that it holds 2 electrons, and this one looks like its shell, its orbital, its ring is filled all the way, which means it's very stable, which is a key thing to remember when it comes to understanding how they act. Down here on the bottom, we see something a little bit more like reality. We can see the nucleus contains the individual pieces, the protons positively charged, the neutrons with no real charge, and then around the outside we can see that there are 2 electrons. This is still helium, and I know that because there are 2 protons here, and helium has in fact 2 protons. And we know there's 2 electrons hovering around it, but we can't like point them out. We don't know where they are. And the thing is, they don't actually revolve in a perfect circle. The cool thing is they actually go around in really cool kind of loops, kind of teardrop shaped, very unique. And if you take chemistry, you will learn all about those orbitals, which are fascinating. Here is probably the best tool ever designed with just one piece of paper. This is called the periodic table. Hopefully you've seen this before, and I just want to show you a little cheat sheet to help you understand exactly how many valence electrons, how many extra electrons, or even how many protons, or in general how many electrons you find on an atom. So let's go ahead and look here at our very first atom. That's going to be hydrogen. Hydrogen has the number 1 here. Now, when you look at other versions of the periodic table, each one of these boxes are filled with a lot more information, tons and tons of numbers. And for right now, I just want you to point out something called the what we call the atomic number. Okay, the atomic number, and that simply equals the number of protons found inside of that particular atom. And atoms with different number of protons equal different elements, and they all have their different behaviors and characteristics and properties. So hydrogen is going to be number 1 on the periodic table, and you can find that right there where we pointed out. That means it has 1 proton, and I just know from just previous experience, it has no neutrons because it's just such a simple atom. It's the most common thing in the universe, but it also has 1 electron. So one basic rule, very general rule, it's not always true, but your number of protons, okay, roughly equal your number of electrons. So this kind of makes sense because you have like positive parts and negative parts, and you would like them to balance out to be kind of neutral, kind of balanced. So what we find there in hydrogen, 1 positive part, 1 negative part equals overall nothing. So that's going to be kind of how they're balanced there. But hydrogen is very likely to make bonds with people, and there's a reason why. That's because when we look at hydrogen and we look at its ring that goes around here, we know it has 1 electron on the outside because it's got 1 proton, so it's got 1 electron, and there's this extra space. Now the key thing about these spaces, these orbitals, is that they want to be filled or totally empty. And in this case, hydrogen wants to get filled, which would mean it wants to gain an electron, which can mean it wants to do some cool stuff. So it means it wants to bond with things. It wants to act in a way that can make it happy. Let's go ahead and look over to the opposite side of the periodic table. Right up here, we can see we have something called helium, which we just talked about in the last example. And we said helium, He, on its outer shell has 2 electrons. So if we look at that number, its atomic number is 2, which means it has 2 protons, and that means probably we expect it to have 2 electrons, and in that case it is very much true. We always find helium with 2 electrons on the outside. It doesn't like to lose them. It's very happy because its outermost level is full. Another cool thing to realize here is that we don't actually have to break this down and remember all these crazy numbers. But I'll show you that here in a second. So let's talk about carbon. Carbon, which is essential for living things, carbon is number 6 on the periodic table, which must mean it has what we expect to find 6 electrons. So if we go ahead and draw that, and let's say we got carbon, we're going to draw a ring around here, and then we're also going to draw a ring around again, and I'll tell you why. Because we find 6 protons and 6 electrons. So if we start working inward to outward, we have 1 electron here and 1 electron here, right? Okay, that makes sense. I'm going to redraw that circle because it was terrible. Hey, that's a little bit better. So we've used 2 of the 6 electrons we know carbon has. So then we start adding them to the next layer, which would be 1, 2, 3, 4, and we ran out. Now, if you remember back earlier, we said our shells can hold up to certain numbers of electrons. The innermost shell can hold 2, the next shell can hold 8, and the final shell can hold 8. There's actually way more than this, but for all of our purposes here in biology, we're probably not going to play around with those, so don't worry about memorizing them quite yet. Anyway, so this means there's a space saved for that electron. There's a space saved there, there's a space saved there, and there's a space saved there. There are 4 extra spaces until that fills up. Carbon wants to make those bonds. Now, how can you predict how many extra electrons it has on the outside? Well, that's quite easy. If we actually look at the very top, we have these things called groups, and there's a little cheat sheet kind of built in. If we find here, we see the number 1, 2, 3, 4. Well, let's go ahead and look at this. Right in this range up here, we're just going to look at the top portion of the periodic table, okay? On that top range there, we find the number 1, 2, okay? This entire column right down here is going to have 1 valence electron. The next column, the next spiky one, the taller column, is going to have 2 valence electrons, which matches up to the group number. Now, we don't play around with these kind of guys down here. They're flat, so we don't really mind too much right now. So we're going to kind of ignore all of them through this number. And then we'll just go ahead and start over on number 13. And that means they have 3 valence electrons, and then 4, 5, 6, 7, and 8. And that makes sense. Now, another cool thing is if we look on the up and down rows, that's going to be 1, 2, 3. These are called periods. So our first period here has how many elements in it? Well, that has hydrogen and helium if we go all the way across this way, which means it can hold 2 in its innermost shell. Oh, look at that. The next one, starting with Li, lithium, and then Be, if we move forward, we're going to count those elements. 1, 2, 3, 4, 5, 6, 7, 8, just like our second shell of orbital, or how many electrons our orbital can hold. And then for our third period, it can also hold 8, which kind of corresponds to that idea of 2, 8, 8. So that kind of fits that ideal together. That's one way that you can use the periodic table to predict the number of valence electrons, the extra electrons found on the outside. Soon we'll talk about why those number of valence electrons are so important. Actually, let's go ahead and talk about it now. Those very important things are because atoms form bonds with other atoms. Now, there's 2 strong type of bonds out there. The first one is called a covalent bond. Covalent bond just basically means they share electrons. That's the key word that you want to keep in mind. They share electrons. Covalent shares. That means one atom might borrow the electron sometimes, the other atom might borrow the electron sometimes, so they can both pretend that they have their outermost shell closer to full, so they're much happier. So they decide to share, which is nice. Very strong bond. And then we have ionic bonds, and ionic bonds are when atoms give up or take an electron from a different atom. And this will cause a change in charge and will all overall make them stick to things that have opposing charges, which is, once again, a very strong bond, but just not quite as strong as a covalent bond. You deal with things that are ionically bonded all the time, too. So let's go ahead and talk about those. A covalent bond, we're going back to our example of carbon here. I just want to mention that we said that carbon on one of our previous slides had 6 valence electrons. That means 4 valence electrons, and that's 6 electrons overall. And you might remember we drew it with 2 circles, and in this example here, they just didn't draw the centermost orbital because it's kind of filled. It's already happy, so it's just kind of extra information. But anyway, the blue dots represent the electrons from carbon, so there's 4 there. There's the 4 valence electrons, and then we have hydrogen, which we talked about earlier too. And hydrogen has 1 electron. So what they do is they both have their shells that want to be filled. So hydrogen only has that first shell, which can hold a maximum of 2, and in our example here, we can see it's sometimes borrowing the one from the carbon, and sometimes, hopefully always has its electron, so they can actually fill that outermost shell most of the time. So hydrogen likes this bond because it's happy, and that's true of all the other hydrogens that we find here. They like to bond by sharing them. And carbon is very happy as well. Now it has 8 on its outermost shell. So you remember the inner shell goes 2, and the second shell can hold 8. And if we count the number of electrons there, it is holding 8. So it is satisfied. It is happy. An ionic bond is a little bit strange. Basically, we're going to be working with another element here. Na actually represents something called sodium. Yes, I know the name and the abbreviation there do not quite match up, and there's a reason for that, but for right now, just try to remember Na is sodium. Sodium has 1 valence electron, so you'll remember the shells go 2, 8, and 8, and it has 1, which means it appears on the first group in the periodic table. It has 1 valence electron, and that is just, of the 8 that it wants, just having 1. Wow, that's such a way to go. Actually, sodium would be much happier if it just lost that last electron, because it would be so much happier because its next outermost shell would be totally full. So it'd be, oh, I'm all happy, I'm filled up. Now remember, if we lose the number of electrons, we don't change the number of protons in the nucleus, so that creates an imbalance in charge. So when sodium loses that charge, that negative charge in the outside, we still have the same amount of positive parts on the inside. So I know, for instance, sodium, Na, has 11 protons, okay? And in this case, up here, it also has 11 electrons, which overall creates a negative charge. But down here, now we see it has 11 protons still, but now it has 10 electrons, which overall gives it a positive 1 charge. That's actually why this little positive symbol is now written next to Na, because it represents that it has a positive charge because it's missing an electron. Cl, which is going to be chlorine, is going to have kind of the opposite side of that problem. It really wants another electron. Once again, the shell's 2, 8, and 8. It is so close to having a full outer shell, and luckily, if it's in a solution that has sodium floating around, sodium might break off one of those electrons, and chlorine is going to steal it. So it's going to add it to its outermost layer. So it's very satisfied. But once again, keeping that basic math in mind, chlorine has its number 17 on the periodic table. It has 17 positive parts, and it would have 17 electrons, which overall would be a neutral charge. But now it's going to gain a negative charge. So it's got 17 protons still, because that's in the nucleus, and that never changes. And then it's going to gain 18 electrons, which means it's going to overall gain a negative value. That's why Cl is written with a negative symbol up there in the corner. So now that they're like this, and we got a positive and a negative, well, in nature, positive and negative seem to attract to each other, and usually pretty easily. So they will stick to each other, and they will form an ionic bond. So let's start talking about the idea of water. Water is what we call a polar molecule. Now, a molecule is just 2 atoms or 3 atoms or however many atoms that are sticking together through a bond of some kind. Usually it's going to be a covalent bond, by the way. So water is basically an oxygen and 2 hydrogens, and they kind of stick to each other like this. Now, of course, you guys should know the formula for water is H2O. And that's actually where we get that from, is because there's 2 hydrogens attached to that oxygen. There's no 1 behind the O, just because we just kind of assume, oh, well, that's kind of already understood. If you just have the atom, you just have 1. Anyway, overall, we have 2 different charges on this side of the atom. This is called polarity. Okay, so that means the oxygen here is going to be slightly negative, and the hydrogens overall are going to be slightly positive. This means water is attracted to other water molecules, or polar molecules are actually attracted to other polar molecules. So once again, let's just say we've got our oxygen, and we've got our hydrogen, and we've got our hydrogen, and we said, you know, the hydrogens are going to be positively charged, the oxygen will be negatively charged. That means if we have another water molecule nearby, it might want to stick to it like this, with the oxygen side now facing that way. Now, anyway, we know that water likes water. We'll even define exactly what that means here in a little while, but just try to keep in mind water is a polar molecule, oxygen is negative, hydrogen is positive, and it looks kind of like that. And I'll show you a better picture here in a second. Now, the reason why water looks like an upside-down Mickey Mouse head is because water is sharing electrons between the hydrogens and the oxygens. Okay, so here on the left side, you can see kind of those orbital shells that we were talking about earlier. Once again, remember, we have 2 on the innermost shell, 8 on the second shell, 8 on the third shell if it were there. And for the hydrogens that we both have here, they only need to hold 2 on that innermost shell. So we can see here that they are sharing electrons, right? The hydrogen already comes with 1 proton and 1 electron, and it wants to borrow an electron sometimes from the oxygen. Now, that's happening in 2 instances here, and we can see that's happening, but I should also point out to you, when we just look at a snapshot of the molecule, overall, if we were to just like kind of draw a dotted line through here, most of the positive protons are found here and here. Okay, so they're kind of just hovering on this side of the molecule. Whereas most of the electrons, because oxygen is so selfish, it's so greedy, that it just kind of pulls all those electrons towards it. That means there's a lot more negative pieces in the molecule overall found on this side of the molecule. So that's why it's more negative. We do use a cool little symbol here to show something, that little negative symbol that we find here and here and here, the positive symbols. Those represent what we call electronegativity, and it just means different charges on the sides. There are things out there called nonpolar molecules. Now, water is not nonpolar. It is a polar molecule, but other things out there do exist. And this means they just have differently charged regions on them overall. It doesn't mean that it has just different sides. It could mean it's overall positive or it's negative, but it's not going to have both. Fats, you're probably aware of fats. They're really good examples of nonpolar molecules. Or oils. Now, what happens when you try to mix water and oil? Well, you're probably thinking about it now. They don't mix very well. So one rule that you want to keep in mind is polar likes polar and nonpolar likes nonpolar. So like dissolves like, meaning it'll break it down. They'll mix together. So water and oil, they're not the same way. They're not polar and polar, they're polar and nonpolar, so they don't mix very well, like the picture here. When you mix water and oil, they clearly separate out. You even notice that they have different properties. The oil here is going to be less dense, so it floats to the top of the water. This is actually right after it's been poured in there, and it'll all start to float towards the top and separate and kind of really pull away from that water. So they do not mix together very easily. There's another kind of there's another kind of bond out there called a hydrogen bond. Now, this is actually considered a weak bond, and it's basically going to be the attraction between slightly positive hydrogen atoms and slightly negative oxygen atoms, and maybe sometimes nitrogen atoms. So you'll remember earlier we were talking about the oxygen molecule looks like Mickey Mouse, right? And we said overall it has a negative charge and a positive charge. And I drew this earlier, and I drew, let's say we have another water molecule nearby, and we said this side has a negative charge and a positive charge. Well, there's going to be this little attraction that happens right there. That's what we call a hydrogen bond. Now, I said these were weak bonds, but that doesn't mean they're not important. They don't only exist in water because there's a lot of polar substances out there. For instance, a lot of the molecules inside of your body, like proteins, they form bonds all the time. And some of those bonds that are kind of holding the shape of the molecule together are hydrogen bonds. And they are essential. They're not very strong, but in high numbers, they have a huge influence on how proteins work, on how your DNA works, and we'll talk all about that stuff a little bit later. So as I was mentioning to you, you can see the solid lines between the oxygen and the hydrogen. Those are going to represent covalent bonds. And the bond that's just kind of like a smaller, weaker bond between the hydrogen and the oxygen of another molecule are going to be considered a hydrogen bond. Try not to get too confused on that. I know hydrogen is involved in the covalent bond there, but only when the hydrogen's positive charge seems to attract another object's negative charge do we actually form a hydrogen bond. And these bonds are really the most important things about water. Since water makes these kinds of bonds, it gives it some very special properties. Another thing to note about the hydrogen bonds water makes is that there's a limit to how many bonds it can make at one time. This three-dimensional image kind of shows you that the center water molecule is making up to four hydrogen bonds. So the first bond here, of course, we have the positive hydrogen and we have the negative side of another water molecule. And then this hydrogen has a positive charge, which is meeting up with the negative side of another water molecule. Now we have that, we got to remember that oxygen's a very large thing, so it's got some space to be able to hold things. So there's a negative side there that's matching up with the positive side of another, and then the negative side here, which is matching up with the positive side of another water molecule. So it can hold up to 4 hydrogen bonds. So let's talk more about what these bonds actually do. Now, these hydrogen bonds, once again, is why water stays liquid most of the time, because they're constantly forming and breaking and sliding around, knocking into each other, and they can make up to 4 of those bonds, but sometimes they make even less than those bonds, each water molecule. So it gets to be quite dynamic, and that's why it's usually a liquid. It's very fluid most of the time. But coming up, we're going to talk about 5 special things about the hydrogen bonds, about water molecules, that makes water so unique and so special to us. And downright, it makes it super weird. The first phrase is called high specific heat. Some people call this something a little bit different. Some people will call this heat capacity. Okay, whichever way you want to remember that, that's cool with me. But high specific heat is when water resists change in temperature. And it means basically water has to absorb a lot of energy, a lot of heat, in order to see an increase in temperature, or it has to lose a lot of heat before it changes temperature. And this is really important when it comes to us because it maintains our body temperatures very well. It makes sure our cells don't suddenly change temperature, which would be really dangerous. Think about this. Let's imagine you're at your house, you want to get some ice out of the freezer, and you reach your arm inside and it's cold, it's below freezing in your freezer. Well, the water that's inside of all of your cells doesn't just suddenly turn to ice because you reached inside of the freezer. If that happened, well, we wouldn't be able to experience those extreme temperatures, or not even that extreme of a temperature change. So that would be really dangerous and we wouldn't be able to survive. So thank goodness it doesn't. I can stick my arm in a freezer for hours and hours and hours. It wouldn't be very fun, but I could stick them in there and not all the cells would freeze up. So that's very important. Also, if it's very hot outside, if it's above 100 degrees outside, I don't suddenly lose all the water outside of my body. I can walk into an area that's well above. I can reach my arm inside of an oven, a hot oven, for a very brief period of time, and still the water doesn't suddenly evaporate or vaporize and turn into steam. That's once again because water resists change in temperature. The next property is called cohesion, and this is the attraction of a molecule to another molecule of the same substance. Now, water likes water, and that's what it's called, cohesion. So when water likes water, it's called cohesion. This is actually why water beads up on windows and forms the droplets. If you've ever noticed, like going down the road, you'll notice a lot of the times they'll form a common stream, and they'll stick together. It doesn't just spread out evenly across the surface of the glass, and that's because it likes water. This actually leads to a very cool concept called surface tension, which means water doesn't like to pull apart too easily because it's forming those hydrogen bonds. It likes water. This is what makes belly flops whenever you jump into a pool. Makes belly flops hurt so bad is because that water, as you're hitting it, doesn't want to move, and you're hitting it with such a wide area, it can't move out of the way fast enough. So it hurts really bad. This is a water strider, and these water striders are known for kind of walking on the surface of water. And they're not very heavy, but they do a really good job on distributing their weight because their bodies will not actually be having enough pressure to break through those bonds, those hydrogen bonds found on the surface of water. In our class, what we did is we actually did a lab where you dropped water on the surface of a penny, and you counted how many drops were there. In one version, there was just pure water, and in the other version, there was salt water. Well, the one that didn't have salt, the one that was just pure water, had more cohesion, which means more surface tension, which means there's more bonds, more hydrogen forms forming between those water molecules. Now, the other side of that is the idea of adhesion. Adhesion is when water molecules are attracted to other substances or different substances. This is why water seems to climb up the edge of a test tube. If you've ever done any kind of measurements before and you've played around with, terrible line. If you've ever done any kind of measurements before and you've used something called a graduated cylinder, you would actually notice like there's little marks on the side and you can measure things. But water doesn't just lay flat across what your measurements. Actually, it kind of curves downward and looks like that. We call that a meniscus, and you actually have to measure like that across what the bottom of that bubble seems to be. And that's because the water on the edge of that tube wants to climb up and stick to the glass or the plastic that's there. So that's kind of making things a little inaccurate. Also, this is why plants are so effective at absorbing water, is because the material that the plants are made out of absorbs water. It's designed to. I should also point out to you there's a force, an activity that takes place in plants called capillary action, which we'll investigate here on the next slide. So, of course, trees. Trees have roots that are buried, pretty deep into the ground, and they're designed to not only anchor to the tree to the ground, but absorb the water. So we can see the water will move up through the roots, up through the trunk, and then over to the leaves, which are at the top of the tree. Some trees are extremely tall. We're talking dozens and dozens and dozens of feet tall, sometimes hundreds of feet tall. And still, there's not some magical pump inside of the tree that's pulling the water up. It's actually this tissue, this vascular tissue that we find here on the inside of the tree. And we'll talk more about this later in the year. But anyway, if we were to look inside of each one of these individual tubes, what we would see are these water molecules being attracted, in this case being attracted to the side of the material, of the plant material, and then other water molecules want to form hydrogen bonds and connect to the original water molecules that moved up. This is both adhesion and cohesion at the same time, and that's actually what distributes water around in plants. We call this capillary action. And that's a really cool concept and a very important one to remember in the future. A couple things about hydrogen bonds and water in general is that water is considered to be the closest thing we have to a universal solvent. It's not really, there isn't really a universal solvent. There's not one thing that dissolves everything. But water is the closest thing we have to it. And by the way, ions and molecules, they really don't form in a non-water environment. We kind of have designed a lot of life on Earth to work in a watery environment because it's so nice and so good for being able to break things down. Big molecules actually have to be dissolved before they can move and get used in the body, and that's why we are so full of water, or at least one of the reasons. So there's not really a true universal solvent, but water is the closest thing we have to it. Another really cool thing about water, probably the weirdest thing about it, is that when water freezes, it expands. And this is because the energy within those molecules has basically started to slow down, and it allows for these hydrogen bonds to stay in place more permanently. And when they're forming those bonds, they're not sliding past each other and getting close and far away and breaking. What they're doing is they're evenly spacing out. And this is kind of nice because it actually serves as an insulator to other organisms or living things, especially in water systems. So like in northern regions in the United States or Canada, every winter it gets very cold, and we see lakes and streams, ponds, they all will freeze over. But that doesn't mean all the water inside of the lake froze. It just means the top layer. And the things that were living in the lake, a lot of them survive because they just stay below the ice, which is still liquid. And that cold air outside has basically been blocked from making the rest of the water even more cold. So it's a very cool feature that we find, and it's actually been responsible for doing things in like eroding material. There's something called ice wedging, if you ever took a earth, space, or geology class. Basically, if water gets into a crack and then it drops below freezing temperatures, the water will expand and actually cause rocks to break open. This is actually pretty annoying when it comes to winter months, especially in the north, because you get cracks in roads that just inevitably show up. Water gets in there, freezing happens, and then you start breaking up the rock or the asphalt and the gravel that was holding the road together. So it actually requires a higher upkeep cost. So in our little diagram up here on the right side, you can probably guess this is when water is going to be in a liquid state, and you can see the hydrogen bonds. They're not all the water molecules here are making 4 hydrogen bonds at once, and sometimes they're very close together, sometimes they're very far away, and that means because they're constantly moving, they're bumping into each other, they're going to be a liquid state. Over here, we can see we have ice, which is the solid version of water, and you can see that all of the hydrogen bonds are forming kind of a lattice, kind of a nice even spacing, and they all have the same amount of distance. They all are going to be maintained and held in the same place, and that's what makes it a solid. And you can see all of them have that, they just use the 3 dots to represent spacing here. All of them have 3 dots, which means they're all the same distance away, which on average is slightly more space being used than the liquid water form. So living things like our little shrimp down here, he's not really a shrimp, I can't remember what he's called, but our little guy here can live in the liquid portion of a frozen over lake, maybe take in some air bubbles that's being trapped by the ice, and continue to survive kind of unimpeded, which is a nice feature for life. So we have been using this phrase, solutions. You'll hear us using it through the rest of the year. But a solution is going to be the mixture of substances that is uniform throughout. Most of the time, you can't distinguish one part from another, multiple molecules mixing together. There's 2 parts to this, okay? The first part is called a solvent. The second part is called a solute. Now, the solvent is going to be the substance usually in the greatest amount, and it dissolves everything else. So in most cases, the universal solvent is going to be water. So in almost everything in biology we're going to work with is going to have solvents be water. Solutes are pretty much everything else, and those are the substances that are being dissolved. So when you think about the can of soda that we see down here, delicious Surge, these components are going to be like the main ingredients. So the main ingredients of soda could be water, of course sugar or high fructose corn syrup. You've got things like sodium citrate, sodium benzoate? I can't remember. But the point is, lots of things are inside of soda, mainly sugar, and water. Well, what breaks down and dissolves the sugar? That's water. Therefore, water is the solvent, and everything else is going to be the solute. For a glass of iced tea, the same thing is true. The main ingredients are water, sugar, and pretty much a tea leaf that's been crushed up. And once you add the water to it, you dissolve the leaf, you dissolve the sugar, the water stays pretty much water, and it allows everything to mix together. Therefore, water is the solvent. Solutes are going to be everything else in the glass of tea. So once again, just to show you there, water and sugar, in this case, will mix together eventually, and when they do that, once they diffuse, we're going to have the result of a solution, which will be a sugar solution in this case. And pretty much you name any solution, basically what the solute is floating around in it, and usually most of the time you tell us what percentage you find that solution. So that maybe we could pretend this is like a 10% sugar solution. That just helps people understand exactly what's in your mystery solution. Now let's go ahead and seem to change gears here, but trust me, it actually does fit in with the idea of water. We're going to talk about acids and bases. Now, acids are going to be things that have higher amounts of protons floating around inside. If you have fewer amounts of protons floating around, they're going to be considered a base. Now, this actually relates directly to water because most of the time things will ionize in water, and we end up with these free-floating protons. Basically, what that means is we end up with a lot of hydrogen protons floating around. So if you see a high amount of hydrogen protons, we get something that's an acid. If you see very few hydrogen protons, that's going to be a base. So you've probably heard of acids and bases before, and you know acids are really dangerous, and maybe you're not exactly sure what a base is, but they're basically just representations of the number of protons that we find. Now our scale goes from 0 to 14, okay? I know it's not 0 to 10, it's 0 to 14. I know it seems like a strange number, but it does make sense. And right there in the middle is the value of 7, okay? The water that we've been talking about, just pure water, is hovering right around there in the middle, around 7. The strongest acids we find are going to be found on this side. Okay, the weakest acids are going to be really close to the 7, and a moderate acid would be found in between. For a base, the further away from 7 we are, okay, the stronger the base. So that would be a strong base, and a weak base would be closer to the 7 again. And then in the middle, of course, that'd be a mild or moderately strong base. So the closer we get to 7, just try to remember that it becomes more neutral or less reactive in some way. There's actually a whole nother scale. This is actually called the pH scale, as you can see written here. There's actually another scale out there called the POH scale, which basically measures how much of a base it actually is. But we know if you're not very much of an acid, I guess you must be more of a base. But anyway, this scale is pretty representative of what we see for those properties. So I was mentioning earlier, we have those hydrogen protons floating around whenever we have an acid. So acids are, the strongest acids are found towards 0 and 1 on the scale. Battery acid, of course, is extremely strong. Stomach acid, the stuff inside of your belly right now, helping you digest your food, is very, very, very strong. And if you actually look on this side, it says 1,000,000 times stronger than just plain distilled water, which is pure water. Now, you'll also notice on the left side here, it says the hydrogen ion concentration relative to pH 7, which is just a fancy way of saying it's a logarithmic scale. So every time we move up on that scale, it goes up by a factor of 10. So if we move up 2 places, it goes up by, instead of just, let's try this again. It would be 10 to the first power here, 10 to the second power here, 10 to the third power here, and remember, anytime you have an exponent there, it just means that number times itself again, and again, and again. So we basically see how much stronger acids become than just plain water doing that. And then we see the exact opposite being true. So, when we're looking at this side of the scale, we see 10 to the negative first power, or 10 to the negative second power. So all we're trying to describe here is we are showing how many positive hydrogen ions are floating around. On the base side of things, you'll also notice a lot of cleaning agents will be found down here, and they work really well to actually destroy like cells and nasty stuff that's kind of stuck to things, so we can clean them off, and hopefully we don't get sick or cause any problems later on. This is the same scale. It's still the pH scale, but it also just shows you some common things, especially thinking about the environment. This has been pulled from the Canadian government, and we can see there's that range right there in the middle. There's our neutral value, and milk is slightly acidic, and we're talking about just like normal stream water should be in a value found right from here to here, hovering close around 7, because of course it's water. If we see like normal precipitation, it's slightly acidic. But I'm sure at some point in your life you've heard of something called acid rain, which is anything that falls in the range from around 1 all the way up to 5. Now, if we have a lot of acid precipitation, we can actually start to see ecosystems be directly affected. And we'll talk a lot more about this later in the year, but just to point out to you, fish reproduction is affected around 4 to 5, and basically adult fish will die around 3 to 4 range, which is pretty much the equivalent of vinegar. I'm sure you wouldn't want to swim around in a pool of vinegar, and fish don't either, and that would actually lead them to die. So knowing a lot about the acidity of water sources plays a role in not only just ecosystems, but overall the planet's health, as we talk about something known as climate change. Once again, to show you the effects of acid rain, and we'll end it with this. This is actually a forest found in the Czech Republic that has experienced years and years and years of pollution from an upwind source, and of course the wind is carrying clouds that are filled with precipitation that have probably gotten some condensation nuclei from the smoke or the pollution from those factories that have created this stuff. So they are creating acid rain, and it's falling on a forest, and you can see things don't look exactly too healthy on these trees. Their bark is clearly being eaten away, their branches are worn down. It doesn't seem like these things have a chance to survive all that well, and that's because of the unbalance of acid in the soil and on the surface of the tree. Okay, so that was pretty much everything for chemistry and for water. I know we took a nice, long, crazy little roller coaster there. Thank you for listening. If you have any questions, just let me know in class, or just make a comment later on. All right, have a good one.